Hello everyone, my name is Anshumadikami and welcome back to part 2 of SIT221 quiz tutorial. So in this video, we will cover part 2 or week 11 content, which is NP and P problems or non-polynomial and polynomial problems. So what are NP and P problems? NP, or non-deterministic polynomial time, refers to a classic of decision problems where solutions can be verified in polynomial time. This means that given a solution, we can quickly verify its correctness. Polynomial time, or P, refers to a class of decision problems where solutions can be found in polynomial time. In other words, the time it takes to find a solution grows polynomially with the size of the input. Now, that basically just boils down to meaning P problems are solvable, realistically speaking, and P problems aren't exactly quite like that. So there's different types of NP problems as well. There's NP hard, there's NP complete, and there's just the normal NP one as well. Now, some of the main differences between NP and P is that NP problems can not be verified in polynomial time. This means that while it's easy to check if the proposed solution is correct, finding the solution itself might be challenging and time-consuming. P problems, on the contrary, can be solved in polynomial time. This means that efficient algorithms exist to find solutions for these problems quickly, even as the input size grows. So, for example, all the problems we've done in this unit have been in P problems. So none of them have exactly been NP hard or NP complete problems. Everything has been going in, or at the very least, all the end solutions are in polynomial time. If some of you guys have completed the distinction task for 8.2, you may have noticed that when you start off your algorithm without dynamic programming is an NP problem because it is an exponential problem. So when it comes to the big O notations and the polynomial and the non-polynomial differences, anything above a n to the power of x is considered a non-polynomial. So even NP100 is counted as a polynomial time. However, 2 to the power of n is considered a non-polynomial, and so is n factorial. But anything below that is considered in polynomial time. So n log n log n, even n square, all of that is polynomial time because we can actually find it. And those of you who have attempted 8.2 can probably verify that no matter what happens or how long you let your computer run, a algorithm with a 2 to the power of n complexity with a large enough n will basically never complete, which is where we come down to some examples. So please take a look at the examples very carefully as these will be relevant in the quiz. So we have the Hamilton cycle problem, 0-1 knapsack problem, subset sum problem, traveling salesman problem, graph coloring problem, and shortest path problem. So these are just some of the most common NP hard problems and NP problems. So some of these ones like Hamilton cycle, 0-1 knapsack, these are NP hard, while some of these aren't. So shortest path could be just an NP problem. Now, taking a look at the difference in the Venn diagram, NP, NP complete, NP hard, and just P. So right now, P is not equal to NP. Please keep that in mind. P is not equal to complete. As you can see, P is inside of NP. So if anything, P is a subset of NP. And NP hard is a set of itself, a set of problems in itself. And NP complete is somewhat correlated with NP and NP hard as well. So it's like the middle ground between these two diagrams. Now, what we mean by NP complete and NP hard is that NP can only be solved in non-deterministic polynomial time, such as determining whether two graphs can be drawn identically. And no NP complete or NP hard, at least, as hard as to solve as the hardest problem in NP, which would be some of the examples I showed before, such as the traveling salesman problem. NP complete is when there's no fast solution is known, such as the knapsack problem. Now, what makes the difference between an NP hard and NP complete is figuring out its non-deterministic polynomial time. So making an NP hard problem uh, doable by a non-deterministic Turing machine. So let's go back here. Let's take the knapsack problem. So we know that this is a NP hard problem, and to turn this into an NP complete problem, we will have to use something called similarity. So you can see there's a lot of NP hard problems, right? We don't want to just tackle each of them one by one, like have like two researchers on this, two researchers on this, but we want to make sure that if we can complete one of, or if we can solve one of those NP hard problems, we can practically solve all of them. So to do that, we have to relate each of these problems with the other. So we can do that by calling something called like a singularity or a similarity. So I think it's called similarity. Let's just call it SI. Let's just say there's a problem. You can check out the week 11 lecture recording to get a better understanding of what this is. Nair does a fantastic job at explaining it. But let's just call it a magic complex algorithm. And let's say that if we manage to relate this magic complex algorithm with all of these algorithms and say that, okay, the traveling salesman problem is similar to this in the sense that the solutions can be similar. Uh, I think one of the examples that Nair used was a magic function. So these have similar magic functions. That's kind of what this entails. And that if we can solve this, we can solve all the ones that it's similar to. That's why we try to make it so that the NP hard problems are similar to this one. So if we can correlate, if you can turn this NP hard problem, or if we can prove that this NP hard problem is similar to this, then we can say that this is an NP complete problem now. And the point of NP hard, NP complete is that the magic function is something that we don't have the ability, research, or capacity to solve. But we are hoping that someone in the future will be able to solve them. So it is very poetic in the sense that people will do years of research just to hope that someone in the future can take that research and actually solve it. So they're kind of essentially preserving their research and giving everyone in the future a head start for their researches so that they won't have a hard time finding the actual magic function, or at least will be able to focus on finding the magic function rather than doing all the other parts of the NP hard problem, which is can be said in the sense that if anyone has seen My Hero Academia, it's like All Might's power where he can pass it on to generations, entrusting it to the future. And every generation, it gets better and better and better. And similarly, the NP hard problems get handed down to generation after generation of researchers, and people add on to it until it's actually solved. But none of them have actually been solved so far. As I had mentioned, if you solve one of them, you solve basically all of them. Now, this is the future that we want, or this is the future that the researchers who've poured hundreds of thousands, hundreds of hours to hope that their research will be helpful to the future researchers, is that they hope that all the polynomial or all the non-polynomial algorithms or problems are solved in the future. Because that for at least the non-polynomial ones, when you've solved, these are easier to solve in the sense that a merge sort or quicksort at one point was a non-polynomial problem because they didn't know the solution to it. But after they found the solution, it became a polynomial one. And that meant that the P circle grew a bit more. And just like that, we hope that it just keeps growing again and again and again, all the way until P is equal to NP. So that is our future goal with this research of NP and P. And this is our present. So please keep that in mind. Another example could be from the Wampus world when it comes to deterministic and non-deterministic. So deterministic is when the algorithm knows all the states possible. So in this example of the Wampus world, which you might have done in SIT215 as well, generally speaking, Wampus world is a non-deterministic problem where you don't know all the answers. You have to kind of go one by one using your perceptions of smell and feel like breezy or smelly to kind of figure out where the pits are or the wampuses are. So in this sense, you are basically blind and relying on your other senses. But a deterministic one is basically you have full 20/20 vision and you can see anything and everything in the board, which you can see from this diagram, makes it so that the agent just goes straight up to the wampus and just kills it to get the gold without having to rely on wampus or the wampus's smell or the pits. And yeah, that's all for this video. Good luck with your quiz. Thank you.